No, it's okay. Okay. Okay, so the math foundations for the neural networks nowadays used a lot is universal approximation theorem. Okay. And the neural network generated by this universal approximation theorems we called MLP, which stands for multi-layer perception. The theorems tells us if we have a function, okay, and this X is from a compact subset of Rn, we can have this approximation alpha I Wi X I plus Ei. Okay, I is from 0 to n, and this n is depending on what type of how accurate you want the approximation be. Okay, so in other words, it's like if you want if you want 100, okay, theoretically speaking, like the wider your neural networks, the more accurate your approximation will be. Okay. Then there was going to be a problem. Okay, the problem is, okay, I could have infinite nodes, which is the approaches to infinity, but the training cost will be very huge. There was a talk, actually it's banned anywhere in social medias or YouTube. It's standard, it's a Stanford CS class. He invited the former CEO, okay, of Google, and the guy actually said that they were trying to persuade the White House to put more monies for, for training those type of networks, okay? And the cost of that will be $30 billion. And the energy cost will not be getting from US, so they, they were having some strategies either getting from Canada or from, the Middle East, okay? Well, it's gonna, okay, so here's another reason why this new networks draw a lot of attention is, so let's give you the math foundations first. Okay, the math foundation is Kolmogorov. Superposition theorem. Okay. Okay, this Kolmogorov-Arnold superposition theorem is from 1957, I believe. It says for a continuous, okay, multivariate function f, be more precise, is approximate b, but here we have a straight, equal sign. Okay, for a multivariate continuous functions, we can write into a compositions of a single variable functions. Okay. So here, Q, P, and this P is from 1 to n, and this Q is from 1 to 2n. And there was outer functions, which is phi q over here. Okay. And don't feel scared of the representations. I will give you an intuitive ideas of how it's gonna look like in a little bit. Okay, but the representations actually gives us an insight. Is the true multivariant function is indeed a sum of assumptions, okay, of those single variables functions, okay. So, and it's powerful. It's like, so for this case, if we compare, okay, if we compare, this will have in you infinite summations, but this representation tells us we can use a finite, okay. We can have a finite representations for whatever I was given, okay. So here, let's give you assumptions, okay. X is between 0 and 1. And this phi inner functions. The inner functions will behave a little bit weird, okay.
So what are the inner functions? Like, is it like expressible?
Very good questions. The superposition theorems is actually existence theorems, okay?
So you don't know what these phi are?
We have the properties of the inner functions, okay? The inner functions is, if I believe is, we're gonna monatomic 6G's. Okay.
And F is just continuous?
Yes, and F is continuous. Okay, and there's also a phi I, big phi I, which is the outer functions. And this phi I is still not constructible because it is just depends on your function f. Okay. Right. Okay. So that's basically about the Kolmogorov-Arnold superposition theorems tells us. Okay. First of all, I want to emphasize again, it's amazing. It's like, first of all, it tells us for any type of continuous multivariant functions, we can write into a finite sum of a single variable. Okay, but the existence of this has been proved, but how to construct it, especially the outer functions, and how your inner functions behaved is still a problem. Okay, nowadays it's still problems.
So it says x bars between 0 and 1.
Yeah.
I think coordinate-wise, or between 0 and 1.
No, it's between 0 and 1.
So is that xp, or is that just?
XP.
XP.
Okay.
So xp is between 0 and 1.
Yeah.
Okay.
X is, yeah, for any type of, so X is n dimension. Okay. So x1, blah, 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 till xn. Okay. His father, Dr. Kevinson's father, have a book regarding to talk about the details of Kolmogorov superposition, theorems, and also there was a famous problem called Hilbert's 13th problem. Is if you prove the theorems, actually Hilbert's 13th problem is just the corollaries of the problem. I think we're gonna touch this later. Okay. All right. So, well, now remember I have an infinite representation, or I have to say that I have an infinite summations here, I have a finite here. Okay. So does that mean that a Kolmogorov superposition theorem is better than the universal approximation theorems? You can't say this. Okay, you can't say this right this moment. First of all, as I mentioned earlier, these inner functions may behave very bad. Okay, and the second of all, the constructions of the outer functions is still a problem. Okay, it's still a problem. And that's why, with this paper was generated 2 years ago by this 30 years physics, students. His professor Max is telling him, like, do not ever try Kolmogorov-Arnold networks. But He said, if you tell me it can't make it, I will try to make it. Okay, so that's why he make it. Okay, and so let's see how he did it. Okay, so that's the math foundations, and I will give you the frameworks of. Okay, the frameworks or universal approximation theorems is like, suppose we have functions here, and we want to try to approximate. As we know that we can pick different basis functions, for example, like RBF, right? Okay, those bell-shaped functions, and the ideas is gonna be like the more nulls or the more different frequencies of your RBF functions. So for this case, I take RBF, but you can pick like Fourier series or Chebyshev polynomials, etc. Okay.
And like, or you can use like Gaussian.
Yeah, yeah. You can also pick Gaussians as well. Gaussian RBF, right? Okay. So that's basically about this. Okay. But I have to restrict my functions to be at this compact subset of Rn. Okay, this just into 2D dimensions. Well, if we take a look at the Kolmogorov-Arnold superposition theorems, by the schemes of that, we can immediately, or apparently, you can see there's gonna be two layers. Okay, so if you have input layers, you have this output layers. Okay, for instance, if I have two inputs over here, x1, x2, okay? So by the theorems, I may have 2n plus 1, which is 5. Okay, nulls over here. And I have one output here, okay? The ideas of, I think I forget some sigma functions, but I will talk about that later. So the sigma function is actually, for this case, it stands for RBF. For different scenarios, you can switch to different activation functions over here. Okay. That stands for RBF. Okay, now we have this schemes. Okay, so I have. So instead of having a state, instead of having a fixed activation function on each node, now I have something that I can learnable from the process of training. Okay, so here I have the edge, which is phi 1, 1, and this is from phi 1, 2. Okay, same thing for the rest. Okay, remember each of the edge nowadays is not a fixed, which is learnable functions. Okay, I will give you an illustration later on. So that you have the big phi 1, big phi 2, big phi 3, big phi 4, etc. And here is your output. Okay, and okay, those edges are the represented linear functions. And remember, the connections between those inner functions will be just to sum them up. Okay, it's just a summations. Same thing for here. Okay, once you generated these knots from the two inner function phi 1, 1, phi 1, 2, if I evaluate it at the big phi 1, okay, I just sum them up to be x1, x2. Well, if I compared with the frameworks of universal approximation theorems, if I still have x1, x2 as a fixed, as an input layer, this is hidden layer. This is input. Instead of having the learnable edges, for the one that we used, is we having this fixed. activation functions, sigmas on the nodes. Okay, the fixed activation function, what I mean is that if you pick Gaussian RBF, for example, then sigma 1 will be Gaussian RBF functions. And sigma 2 will be Gaussian RBF functions, okay? The things you're gonna learn from each of the training step is the edges, okay, over here, okay? But the edges over here was learning is just the, the coefficients of alpha, okay? But the output will be the same. And for this framework, you can see that as long as I getting wider of my networks, my approximations will be more accurate. Okay. So in this case, I just have an infinite. In this case, I only have a finite, which is by theories we have this 5 nodes in the hidden layer. Okay. Let me give you a very good examples which are generated from this Kolmogorov-Arnold superposition theorems. I think it's very important because later on our proofs or the conclusions we get is going to be okay. So let's give you examples. Okay. So if I wanted to train the networks to learn what is x times y, which is productions of two, inputs. Okay. So you have this input x and y. So what if from there, instead of having 1, 2, 3, 4, 5 nodes by theories, after your training, what you could see is okay. They're having a sparsity properties inside of the hidden layers. Okay, instead of having 5 nodes, you after the training to some acceptable errors, the networks actually learned. Okay, with these 2 expressions. Okay, what is this 2 expression tells us? Okay, it tells us like. Okay, it tells us like, okay, if I want to compute the product, the networks first sum them up, which is take the sum, right? And next, they learn to take the square, okay? That's what the networks learn, okay? So remember, okay, these functions on the edge is always to sum them up, okay? It's always summations, okay? And this little break, okay, I'm sorry, this box, which means that you can see the shapes of the function that they learn, which is the 1D, and which is also the inner functions that we denoted over here, okay? So if you're having the shapes, which is, straight line, which means that it's very interpretable to see this is a function x, and this is it's evaluated at the values of x. Same thing for here, okay? Same thing for y. So for this node, it learned x plus y, okay? And for this node, it learned x squared plus y squared, okay? And now you can see that how they learned from the big phi 1 and the big phi 2 is they're going to square it, right? x1 plus x2, so you're going to learn another shape, which tells you this big phi 1 is the square functions, and this phi 2 is take the negative, okay, of what you ever learned from the inner functions, okay? Then that's how you compute x, y, okay? All right. So this is the examples.
This isn't with like some arbitrary error for the actual.
This is a very powerful network, is because it's interpretable. So each steps you could see how your inner function is gonna looks like, and how you can verify your outer function phi 1 as well. Okay, yeah. So I just given you like the 2 layers for examples. Okay. This is layer 1. This is layer.
It's not equal to X. It's just approximate.
Yeah, for some type of errors. Yeah. Yeah. Well, if you were, if you want to. Well, we're gonna having some questions later on, and then it's gonna lead to the extensions. But let's leave it for a while. Okay. Well, let's come back to this superposition theorems again. If we have the theorems and we have immediately having these 2 layers networks, why people didn't pay attention, or why this networks doesn't work? Okay, because this was from 1957, and even in 1987. Okay, Nelson sentenced Kolmogorov-Arnold networks to death because it said that it's irrelevant to the neural networks. Why is that? Okay, this is just a very simple examples. But what if my functions can be represented by the K representation theorems? Then how are you gonna guarantee this works? Gonna give you a good, representation. I'll say that you have approximations. Okay. Now, this comes to the ideas if we make this deep. Okay. Well, theoretically speaking, that you could. Okay. For example, it's like you want to use a 1D line to fill all 2D, 2D plane. Theoretically, it could be, it could work, but the line will be pathological or ill behaved, right? And you won't want to see it because we want the smoothness, and also the smoothness we will click in is because of this, okay? Theoretically, we can say this, but you can't ignore the bad effects causing from pathological of your inner product, inner functions, right? And how to solve that problems is, yeah, for theories, we can generate it, the inner function and the outer function differently, but for neural network, we treat it as the same idea as, we call it the Chen layer. Okay? So if we have something that it wasn't, not well behaved, what about we getting it deeper? Okay, we're getting it deeper. So this is the idea. Okay, this is the idea to make it deep. Another idea is another insight is from this is the scaling law. Okay, so suppose this is the approximation errors E. Okay, that will be approximately, I'm sorry, this E is about n to the alpha, n to the negative alpha. This is approximation error. And this is a parameter of the total parameters you involved. Okay, and this alpha is called network exponent. Okay, what does that mean is like if you want to approximate n dimensions using k, suppose you want to approximate n dimension multivariate functions and you're using k, say polynomials, you will having the curse of dimensionalities, right? We have so-called of that. So for this neural networks, we have this alpha is determined at, you want this alpha to be larger as possible. Okay, say if you want to approximate a dimension n functions and you're using a d, say these order polynomials or whatever, then this alpha will be determined at this. Okay, but if you realize the Kolmogorov superposition theorems actually could be rewritten into a single variable functions, which means that this d is actually 1. Right? Yeah, it's actually 1. So instead of having this scaling laws to be n to the negative n plus 1 over d, it's definitely be more, it will reduce to negative n plus 1, which means that it's going to converge very fast and then give you a better scaling law. But what function space we're talking about is still open problems. And also the part of the paper, paper's contributors, which are from the Caltech Math Department, they were still working on this. Okay, because there was a lot of assumptions, we haven't given a clear definitions. First of all, regarding to the representations, and second, about the scaling laws as well. Okay.
So what did they do in this matrix? Did they construct
these
inner functions, or what was the big result?
Okay. The big result is, first of all, this wasn't new, and this networks exist for at least 40 years. So this is not new. Okay. This is not new. The learnable function is not new. Okay. Deep learning is not new either. Okay. But if you combine them all together, it will be not, a creative word. Okay. Because I don't know. The reason why he doesn't want his students to do it is because you can't make it deep. Okay, that's the assumptions. But I will talk about how to implement these networks, the algorithmic methods. But that also leads to our extensions. Okay, that also leads to how to implement, how to make this deeper, and how this deeper works, and also leads to the sketch of the proof of extensions for the network discussion. So yeah, back to your questions. They, instead of having the fixed, RBF functions, for instance, they have a learnable functions. Okay, for this case, you see that each steps is learned from different, right? So that's number 1. Okay, number 2 is they having the schemes which will be finite and represented, and they make it deeper to avoid this pathological or ill-behaving inner functions. Okay, and the third of all, okay, they were using the deep learnings. Okay, that's why they combining all together and then implemented in a very fancy way. Okay.
So they're using neural networks to guess out these inner functions? Is that what you're saying?
Yeah.
Okay.
Not guessing. Yeah, you can see this networks. Yeah, for examples.
Yeah.
It's kind of like you can learn from it, but the functions that I was giving is very simple. Okay, but they've tried a lot of functions. They have a conclusion is all the symbolic functions could be worked, approximate or say that represented by this neural network cell very well. Okay. Well, we're gonna go that later. Okay. So before I jump to the extensions, I want to make some remarks or thoughts. Okay. For the surface levels of thinking of these two types of neural networks, okay, I was teaching differential equations. There was a method called parameter variations, right? So if you have a functions that is, say this is the solutions of your differential equations, and we say that what if I switch the c to be another function like cx, it still works, and we try. If it doesn't work, it doesn't work, but if we plug in, we can find another one. Same ideas, okay? Same idea, mathematically speaking, is like instead of having this fixed, not constant, but if I have a fixed functions, what about I change it to be something learnable? I'll say that this functions, this is not fixed anymore. You're learning from each steps, okay? You're learning from each step. So that's the first observations, or say that the conclusions when comparing these two neural networks. And then if we go deeper, if you go through the whole histories of neural networks, there was a lot of debating of the neural networks is more like symbolism or it's more like connectionism. Okay, so starting from 1950s, okay, it's alternating. Okay, the means is like, okay, you know the MLP, which is okay, the perceptions. Okay, for basic, you know, logical, mathematical logicals, like perceptions can do actual. They can't do actual. Okay, so people will say that okay, the neural networks, well, we could only handle it for connectionism. Okay, that's lasts maybe for like 10 years, and then people find like okay, this type of Kolmogorov neural networks. Okay, this actually not the theorems. This network actually could handle actual. Okay, so then people jump to that. Okay, so now we say that a neural network is more like symbolism. Okay, but later on, like people, you know, there was a paper related to the histories of this, but we're like alternating each other by the debating of the new schemes of the network they design. But what we could see cans here, I would say that can bridge. Okay, can plays a role that it could bridge wishfully symbolisms and connectionism when we were talking about neural networks. Okay. For another examples is like we know ChatGPTs or nowadays a lot of AI agent, right? Were very popular, and if you want them to give you a graph, which is just literally by saying to them using natural language, it will give you something which is weird, but it will fulfill the task, right? This is connectionism. But, okay, I give Averroes examples. If you ask ChatGPT which one is bigger, okay, ChatGPT will give you wrong answers, okay? It's because the basic foundations of the neural networks was based on this, okay? Somehow they can't handle connectionism. It can't handle symbolism, okay?
So symbolism is like in setting judgment. It's like it can only understand a language. It can't actually understand the underlying mathematics.
Yeah, I will go even deeper. Okay, the reason why is like, you know, I can't do actuals or they can't having a human logical thinkings of doing this. Okay, but okay, the ChatGPT was trained by the basic foundations of this multi-layer perceptions. Okay, and we know. But the networks was not this simple. This will be even complicated. But we're not talking about this. But I just giving you examples. And then what role can could play? I will say that it could be a bridge between this. Okay. Well, let's go even deeper. Okay, for Okay, let's go even deeper. For the philosophy level, okay, if there exists a God who is the creator, and what type of laws or natural laws he created the intelligence, us, for example, human, for example, then it comes like reductionism and holism. Okay, let's talk about holism first. Holism is like, I do not care about whatever inside of this black box. I only cares about the connections, okay? That is what MLP do. Okay, what MLP is, I don't care about each of the nodes. Each of the nodes was a fixed functions, right? I only cared about what is type of the connections between them, okay? Well, reductionism means that, okay, in physics is like we can split, say the basic particles, right, is having connections in between, and also have his own properties, right? Or for a human as well. How you define a human? You can define a human by his own personalities, characteristics, Or you can define humans as his titles, right? He is a good interpreter. He is a good businessman, right? Those titles, right? So for reductionism, it's like we do not, okay, so this is the can do. We care about, when we design the neural network, care about each particle's work, okay? But for the holism, we do not care what's going on inside. I only care about the connection. And for Ken is we care about the parts. Okay? That leads us to thinking is why those ChatGPT doesn't work very well is because all the math, say we were focusing on functions, right? We always want to be a symbolic representations for functions, right? So that's why Ken works better. I should say for AI plus science. Okay, plus AI plus science. And then there's another reason is like when you're training, okay, for instance, why we're not trust the AI right now is because it's just a one-way communication, right? You having this input, you have the output, there's no interaction. But take a look at these examples, okay? For these examples, you having like a transparent brain, like 3 bodies, right? There's nothing hidden there, right? You can see explicitly what is the inner functions and what are the outer functions, right? And for another way, okay, by the programming, you can, for each type of steps, we can fix, okay? So suppose you having kind of thinking what the function should be looks like, you can fix and interact it with this neural network. Then it's similar like how you trust your collaborators, the same how you trust the AI because of this interaction. Okay.
Wait, I don't see why you can't do the same.
No, you can't. Those you can't.
Are they not just like if you're just using?
Okay, you have some afterwards preparation. Yeah, you have a lot of afterwards preparation work to do. Okay. Yeah, but for this you don't have to. You don't have to, right? Okay. For this, yeah, of course, that when after you write something like you can, symbolism, you using symbolic regressions, right, to get whatever you want. But look at this. During the training, during the communications, right, you can having a thoughts of ideas how it's gonna work. And actually, this paper, they have two comparisons. One is the null theories. Okay, the null theories is the example they compared is the paper that was from Google DeepMind. They use the Google DeepMind to find a theorems based on the null theories. Okay, there was interactions based on that. Ken did the same things, but even smaller parameters, like erased here. Yeah, the scaling law performs better than that. The second is from Anderson. What is Anderson? Isolation. It's from the physics ideas. Okay. Both applications for science works better if you are using MLPs. Okay. All right. So that's basic ideas of the motivations. Part 1. Okay. Why am I interested in and why there's weird names called Kolmogorov mapping theorems is like if you have these theorems, we can actually having this mapping frameworks for the 2 layers networks. Okay, for the 2 layers networks.
Okay, so just so I understand the overview, you're using this superposition theorem to basically put a bound on a number of inner layers or hidden neurons you need to guarantee that you can approximate the function or identify the function, right?
Approximate the function,
This,
not identify. For this, yeah.
Okay, so it's the other way. You're using the theorem to say there exists a number of neurons that you can use to identify.
Yeah. So the powerful things for Kant is it is more accurate. but there was still an open problem. It's about the scaling laws. Second is it's interpretables, okay, based on this design. Okay. Okay. Questions gonna come out. What type of functions? Okay. What type of functions? They did not mention the proof or the basic theorems of what type of functions we could use these networks to represent or to approximate. But the authors having like a shot, like for all the type of symbolic functions, they tried a lot, they may having a good approximation using this can. So this is from, okay, it's not just continuous. Not just continuous. Okay, remember, the Kolmogorov-Arnold superposition theorems have having a requirement for our function. It has to be continuous. Okay, it has to be continuous. All right. So this is observations from the output, and as a mathematicians, I can't say that me as a mathematician, but as a math students, we want to try to use the math language to explain why, okay, to explain why it works, okay. Before I jump to the extensions, I want to mention another things is like what type of symbolic function they have tried. They have tried a lot they even tried the Bessel functions. Okay. And for Bessel functions, even if, okay, first, if any function could be right into this form, then there's no doubt that you can use this networks, right? But for some functions, which is first of all not continuous, well, another thing is not well behaved or well defined, or saying that they tried like 10 types of Bessel functions, and some of them even do not theoretically have a representation form of, Kolmogorov superposition. But instead of comparing with MLP giving you a ridiculous, huge errors, Can's actually giving you a better approximation, even if the function does not have this representation. Okay, so this is the work, the conclusions from that. Okay, so let's take a look at the extensions. The extensions is actually from 1987. Okay, it's H. Nielsen. Okay. It said that there exists. Also, suppose function f continues. And we have, first of all, let me write this representation first. So suppose f, so let's not talking about extension first. Let's talk about the original theorems, okay? So suppose I have a little f which is continuous. So then you have, there exists these 3 layers neural networks. Okay, and we can use this fx could be represented by these compositions. Okay. Okay. So here r is equal to 2d 2n if x belongs to 0 to 1 and it's n dimension. Okay, so I will like to say that for short I to the n, and I is 0 to 1. Okay.
That is the xk.
It's z. I will give you, yeah, I will give you some with, yeah, r equals to z, and this is x. J. Yeah, let's just use the function, for example. Let's just use this for instance. I still use this, denoting this x with n dimensions. And r is equal to 2n, right? It's strictly from the Kolmogorov-Arnold networks. And then this is zk, the inner functions, monotonic. Yeah. Monotonic. And and you can see this as, yeah, this is have summations over here. Yeah, I was just using a different ideas to write it out. I let's be more precise. And this k, sorry, and this j was actually equals to 1 to n. What else? And the outer functions, which is depends on, which is continuous, since this function f, little f, is continuous, right? So it depends on f. On f. So that's it's continuous. Okay. This work has been done like 40 years ago, and the proof, this paper is like 11 pages, I believe. It's just applied that Kolmogorov-Arnold superposition theorem directly. Well, let's see the extension. So,
is there a reason why you use that definition? J plus epsilon k. The definition of k.
There's a lot of updated, good question. There's a lot of updated about the inner functions. First of all, they showed that these inner functions had to be monotonic. And then after a few years, I think this guy extended it to be monotonic and also Lipschitz. Okay. Oh, I'm sorry. This zk, yeah, this phi actually, this phi actually is monotonic ellipses. Yeah. Sorry about that. Yeah. This little phi has to be monotonic ellipses. Okay. So in this case, that you could see, the inner functions in this case is a little phi, right? Yeah, little phi is monotonic ellipses. So if I remember correctly, yeah, it's like that. Yeah, thank you for pointing out. Okay, the epsilon is chosen independent from k. Okay. What is your question again? Sorry.
It always refers to k. What depends on k?
Except for divides themselves. The inner functions.
Yeah.
So then what's the difference between this theorem? There exists neural networks.
Yeah, there is because of the neural networks. Yeah, that's the only differences. But you're gonna see like why it could be extended to the symbolic functions based on our restrictions on the neural networks. Okay, it's not just arbitrary type of schemes that we're talking about with restriction on neural networks.
Isn't that given? Doesn't this theorem give you that there exists neural networks?
Yeah. So this is existent. Yeah, this is originally the theorems. Now we're gonna extend to arbitrary f. See capital F. Okay, but everything else I will keep the same. Okay. Yeah, and then this little gk, in this case, depend on f, but we do not have this assumptions continuous no more. Okay, so let's see the proof. Okay, so before we get into the proof, okay, we have this assumption. So this assumption is that does not exist a finite subset x1 till xn belongs to the in. Did I use n? Yeah, in, such that the summations j to r to n of this mu j is not all 0. And this delta functions, I don't have to emphasize that again. Okay, what does assumptions come from? The assumptions that comes from is how they design, how they implemented the neural networks, but it was not in the paper. Okay, this assumptions is not just unique ones. Okay. I really need to emphasize this again. Okay. Remember that it was a very hard task is to is to interpret this pathological inner functions. Remember that? Okay. And the way is to doing this is, okay, the author tries a different way. Okay. First, he tried regularization. Second of all, he tried to make the grade learnable. Okay, but it doesn't work as well. Okay, now he tried this method, which is he trained like 20 steps, and when he see the distributions, and he see that maybe, okay, for this type of skills, I can refining the grade. Okay, this works. Okay, this works. Okay, so this gives me a little, idea. Okay. So for neural networks, you want to feed your input, and it could distinguish if I was feeding you the different input, isn't it? Right? Okay, let's take a look at this assumption. If I have the input, okay, if there exists this subset of the inputs, like for somehow, okay, it could be the summations of that equal to 0 means that I may lose some informations, or say that some inputs will canceling out with each other, then you're going to causing a bad behaviors of this networks, right? And also, this inner functions, it doesn't behave very well because of this. Okay, this assumptions is generalized. Okay, it's a generalized linear a system of linear equations, right? And but I have to say that this is not the unique ones. Okay, there may be a better. Okay, first of all, this algorithm may not be. This algorithm may not be a good or the best one. Okay, the insights of getting, okay, the inner functions behave well. This may not be a unique approach. Okay, so this is number one. Number two, these assumptions, okay, is just that we want to design this neural network such that, okay, our inner functions of zk will not vanishing any inputs. If I were giving us, if I giving any, any inputs of the x, okay, any inputs of your data or any type of data you feed into the neural networks, okay.
What is the delta?
Delta t is I should not using t, right? Is when t is equals to this, it will becomes 1, right? If it is if it's not, then will be anywhere else. At 0 anywhere else. Yeah. So this delta, right? Yeah. Okay. So once again, this algorithms is maybe not the best ones, but it still works. Okay. But the ideas that we have in these assumptions over here may not be the unique as well. Okay. But let's see how it works for the proof. Okay. So step 1. So if this assumption. So if the assumption holds.
So now we're at the hour and 15 mark. Do you think you can wrap up in the next 5 minutes? How long is it? Hour and 15?
I will try.
Hour and 15, okay.
Okay. So here, assumption holds for f, which is continuous. Okay. In that case, I should say that the bigger f is continuous. Okay. The proof will be the proof of this will be using the contradiction. So if we assume this assumption doesn't work. I mean, assume there exists, okay, such a finite subset, so we can exist x1, xn, such that this equality holds, right? Okay. Then we can define a linear jump functional f. Okay. And this f was determined, and this f is all these summations. Okay, I'll be very fast. Okay. So which means that this so GP works on this f is equal to 0, isn't it? Okay. So which means that this functional is annihilating all the functions f belongs to the continuous. Okay. And next we can construct. Okay, we can by Urson's theorem, lemma. Okay, the Urson's theorem tells us, like, if we have a distinct point in a normal topological space, then there exist continuous functions that can take each of the points, right? So we can construct a continuous function f naught. Okay. So f naught at f naught equals to mu j. Sorry. F naught equals to 1 when mu j is positive, and f naught equals to -1 when mu j is negative, and -1 f naught to be 1 elsewhere. Okay, f naught is continuous, and okay, I'll be fast. So in this case, if the functional that we earlier defined operating on f naught is actually to be the absolute value, which is mu j, and by the assumption this mu j is not all 0, right? Which means that it's not a 0, right? Which is contradiction. Okay, because these functionals we defined, yeah, is contradicted with this part. Okay. Okay, step 2. Okay, the assumptions holds for f is continuous. Now we are going to extend this little f to be capital F. Okay. I'll just giving you a. So this capital F we can write into summations. Sk over kx, and that is equal to k equals 0 r, and this k tau k ckx, that is equal to hk ckx summation. Okay, I will denote the equations 1, 2, 3. Okay. 2 and 3 is very easy. 2 and 3. 2 and 3, if you define a one-to-one mapping, okay, if you define a one-to-one mappings, which is omega kx, tau k, zk x, okay, and then by our constructions, this having a properties if the inputs, the outputs of this have a disjoint range, okay. Pointwise disjoint range. Okay, so there exists such one-to-one mapping. Okay, for the number 3 is what you can just let the k be the compositions of sk times tau k. Okay, 2 and 3 is kind of like trivial. The non-trivial part is 1. Okay. How you can write any kind of functions into this is conditions. Okay. Now that's our assumptions clicking. So, okay. Okay. The non-trivial part is part 1. Okay, how you can rewrite your any arbitrary functions into these superpositions. Okay, remember that this is a neural networks. Okay, so all we trade in here y is if we define this y1 to the yn. Okay, then we say that we could having this type of equality holds is we can define this t as a function that takes the values. Okay, that just takes the values of whatever you input for the x. Okay, and next we can define this functional h. Okay, and we can prove that this functional is well defined. Okay, next. We switch the range. This is how our assumptions click in, is we generalized our range for the y, okay, and then here we extend this functional to be, this is a linear, this linearized functional h, okay, and now we can switch the order with the functional and the summations. We can switch it back in here. And next, okay. Did I define SK? Yeah, I will give you the details of what's SK. SK is depends on F. Okay, SK depends on F, and we can also prove. I'm still working on this part, the proof of this part. Okay, after I generalize the H to be linearized case, and then I switch.
Is there a class here? Okay.
Yeah.
All right. So we have
So yeah, the other end will be mentioned.